Now we have Dwight Hubbard about keeping cool using Raspberry Pi to create a network temperature sensor. Give him a hand.
Hi, my name's Dwight Hubbard. I'm really passionate about using Python. Oh, geez, we're not on the screen here. Yeah. Okay, technical problems. That's not it. What? It's working on here. Oh, okay. Well, while they're working on it, let's get started. Like I said, my name's Dwight Hubbard. I'm passionate about implementing Internet of Things. And when I mean Internet of Things, I mean hardware devices powered by a computer. And I'm passionate about Internet of Things using Python. Right? So, computer powered by Python. Today I'm going to be talking about using a Raspberry Pi, which is a great computer to use as an introduction to Internet of Things, right? To implement a temperature sensor. Hey, everybody give an applause to our AV people. This is great. So before I get into talking about the temp sensor, let me talk a little bit about my cat. Generally speaking, when we do an Internet of Things project of some kind, things break and turn blue. The other thing is, we usually have some inspiration for what we're trying to accomplish. In my case, right, I have a cat. Actually, you can't only have one cat. I actually have more than one cat now. But the cat in the picture, if they ever get it up, is my cat that inspired this. Her name's Kaya. We travel. And if you've ever traveled on long road trips with a pet, you run into situations where you got to take a pit stop. You can't, like, take them home. You're not checked into your hotel, and you want them to be safe. So, being passionate about using Python in the Internet of Things, I decided to over-engineer the problem. So, hopefully we can get this fixed soon. The first thing I did is I decided to use a Raspberry Pi. I had a whole bunch of them laying around like most of us geeks. Raspberry Pis work great for Internet of Things uses. And they're very powerful computers that we can use our development tools we're used to. So they are great for implementing these kind of projects. Hey, hopefully this will stay this time. So the first thing we need to do when we're doing Internet of Things is we need to choose the hardware. Now, the Raspberry Pi, oh, geez, every time I change, it changes back to blue. The Raspberry Pi has different hardware connections. When I'm talking about Internet of Things, we're talking about using the connectors on the board called GPIO connectors. These are connectors that are wired directly into the Raspberry Pi. Now, computers are nothing more than huge networks of switches. When we set a variable, right, what's really happening is a switch or a little EDB thing that holds a charge called a capacitor is being turned on or off. Well, these GPIO connectors allow us to connect a device right up to one of those, which means if we hook a switch up to a GPIO connector, and we look at the value at that GPIO's location, like we would a variable, we'll see whether the switch is off or on. This is really, really powerful because we can hook pretty much any electronic device up to the GPIO headers. They may need various converters, but you can hook up a lot of different things. And that means you can choose from a variety of different pieces of components of different sizes, capabilities, such as the temperature sensor I'm using today. There are versions of it that are waterproof, versions that can handle extremely high temperatures, right? Versions that are extremely accurate, versions that are less accurate but really cheap. So, with this, there are some things that we have to keep in mind. We're connecting directly to the electronics of the Raspberry Pi. And like I said, it's really powerful. But there are some requirements. Unlike a USB bus where you just plug your thing into the USB and everything's fine, when you're connecting the Raspberry Pi connectors, there's no safety net. So you've got lots of flexibility, but you need to pay attention or you can damage or destroy the Raspberry Pi in the process. Mind you, if you pay attention, you're not likely to have any problems. I've yet to burn up a Raspberry Pi, although I do know some people who have. So, there are basically three things we want to look for when we're connecting a Raspberry Pi or something up to the Raspberry Pi's GPIO connectors. The first thing is the component needs to be operational at 3.3 volts. The Raspberry Pi is a 3.3 volt computer. This is significant because for several decades, computers ran with a value of 0, being no electricity flowing, and a value of 5 volts, representing a 1. The Raspberry Pi's GPIO pins cannot tolerate 5 volts. If you apply a 5-volt current to it, you will damage or destroy the Raspberry Pi. So that's basically the main thing you got to be careful of. So you need a component that operates at 3.3 volts. Now the other thing is, all these components that operate at 5 volts don't operate at exactly 5 volts. They'll generally operate over a range of voltages. Some of the components will operate at voltages as low or lower than 3.3 volts, so they'll actually work on a Raspberry Pi or computers that use 5 volts. You actually have to read the specifications for the devices to find out. And of course, if you're using a device that's been heavily used, generally you'll see all sorts of tutorials saying, hey, I've hooked this up to a Raspberry Pi, and you'll know, hey, it will work. The next thing is the component has to be digital. Some electronic components, the electricity flows through them, and some form of environment changes how much electricity flows out. For example, a temperature sensor may resist the flow of electricity differently depending on the temperature, and if you measure the voltage, you can determine the actual temperature. The thing is, the Raspberry Pi doesn't have any circuitry to measure the voltage. You can't use those type of components. They're called analog components. At least not directly to the Raspberry Pi. You can actually add circuits that can read the voltage and then use one of those components. But in this case, one of those circuits actually is more expensive than a temp sensor that's digital. So, and then the third thing, remember these components are changing and sending ones and zeros. They're turning on or off the GPIO pins. And obviously, if it's a switch, that's easy enough. But if we're getting temperature, we got to figure out what code is it using to send us the temperature. We need to be able to decode it. Now, that's going to be in the documentation for the component, but a lot of times the documentation is really complicated. So what we generally want is, hopefully, somebody's written a software driver or a piece of software that knows how to interpret the data that the component is actually sending us. So if you can find a component that meets those three things, you'll have an easy time hooking it up to a Raspberry Pi. So let's look at what I did for our project. This is the temp sensor I'm using. This is a Dallas Semiconductor DS18B20, which consequently got bought by Maxim Semiconductors. That's why it's a Maxim Dallas. You can see it either way. First check mark we just brought up needs to operate at 3.3 volts. In the documentation for this component, it says it will operate from 3 volts to 5.5 volts. Hey, 3.3 is right in the middle, or actually it's towards the bottom, but it's within that range. This component will work, at least at the voltage we require. Second of all, it has to be digital. Now, this component uses a serial protocol. Serial protocols basically mean it's going to send a sequence of off and on, ones and zeros, much like Morse code. So it's basically going to send in code what the temperature is. But the thing is, since it's using off and on, it's a digital protocol. So we can use it with our Raspberry Pi. And 3, the most common operating system on our Raspberry Pis is the Raspbian distribution. The driver's built in. It's actually included as part of the distribution. So the software to decode that is already there. So we have a driver. So there's a few things I would like to point out about this sensor that are really instructive for knowing how to hook things up to Raspberry Pi. First of all, the sensor has 2 sides. You can't really see it from the picture here. One of the sides is flat. The back side, the side that we can't see, is rounded. This is actually significant because you need to know which wire to connect to what. And they're going to have a diagram. But if you don't know which side needs to be facing you, you don't know how to orient the device to match it up with the diagram. So the component's going to have something like a flat side or some sort of notch, or on larger components, it will just have all the pins labeled. But there'll be something to tell you, how do I orient this so I can match up the diagram in the documentation to what's the sensor? And in this case, you hold it with the flat side facing you and the pins facing down. Now, this is a pretty common sensor device. Generally, any device you're hooking up to the GPIO pins, they're going to need power. And power is done by the flow of electricity, right? Electricity is going to flow from the positive to where there's less electricity, or the negative. In order for the electricity to flow, it has to have a place for it to go in and a place for it to go out. So 2 of the pins on this device are for power. One's the 3-volt power input, and one is the ground, which is the negative or power output. And pretty much any sensor device you hook up to the GPIO pins on a Raspberry Pi are going to have 2 power pins. And then finally, you'll notice we have a 3rd wire. That 3rd wire is what's going to send the sequence of ones and zeros that we're going to read in order to read the temperature. So, next up, let's talk about how to hook this thing up. In order to do that, I'm going to use some other components. This picture here is a plastic board called a breadboard. Breadboard's probably the most common board for prototyping electronic projects. It's a plastic board with holes in it. There are 2 sides. All the holes in the same row are wired together. And inside the holes is a spring-loaded connector. If we push a wire into it, it will hold it snugly, but not so snugly that we can't pull the wire back out. So all we need to do to wire 2 components together is plug them into the same row of the breadboard. And if we want to build something else, we just pull the things out and use it again. So this makes for really quick and easy prototyping, or building our Internet of Things projects without us having to do things like soldering and other things, which can take time. Second of all, we need some wires to connect the Raspberry Pi to our breadboard. And finally, this particular sensor requires that a 4.7K resistor, which is a common electronic component, be wired between the power and the sensor pin. So, with those things in mind, we have a Raspberry Pi here. This is actually how we would wire it up. You'll notice that in this picture, the Raspberry Pi is oriented So the pins, the GPIO pins, the wires, are in the upper right corner, and we're looking down. Just like the sensor we're using, we need to orient the thing so we can tell which pin is which. Because if we were to hold the Raspberry Pi upside down, we'd be plugging into the wrong wires, and that could be really bad. All right, so first thing we need to do is we need to plug the sensor into the breadboard. Right? We want to wire things to it, so we put it in the breadboard. The second thing, right, we want to connect power. So there is a wire, and you'll see next to the row of pins, it's kind of hard to see. There's actually a little legend that tells us what each pin is. The first thing we do, the red wire is connected to a pin labeled 3V3. That is the 3-volt power pin. That pin has 3.3 volts of power. So since that pin has to be connected to two things, one, it needs to connect to the power connection of our sensor, and we need that resistor to go between the power and the sensor pin. So we plug it into an empty row. Next, we take another wire, we plug it into the row that we just plugged that wire into, and we connect it to the same row that is the power pin for our sensor. Now our sensor is connected to the power on the Raspberry Pi's GPIO. Next, we need the return for the power. Now, the return voltage, or the 0 volts, or whatever you want to call it, is generally called ground. Now, there's big technical reason, but generally speaking, GPIO connectors and on devices, Raspberry Pi included, will have multiple ground pins. They're all wired together. It doesn't matter which one you use. We happened to pick one that allowed us to put the wire out of the way, so you could still kind of read the legend. But we connect a wire to the ground pin on the Raspberry Pi. And then we connect the other end into the row with the negative voltage connector on our sensor. Finally, we take that resistor and we connect it to the power row, and we connect it to the sensor row. And then we take that middle pin, the one that is going to be providing our sensor data from the sensor, and we connect it to the pin labeled 4. The numbered pins are the general purpose input-output pins. They're the ones that we're going to be manipulating. So that pin is now connected directly to the Raspberry Pi. And we use pin 4 because the driver we're using defaults to looking for a temperature sensor on pin 4. If we picked another pin, we'd have to actually reconfigure the driver, which isn't very difficult, but this saves us a little trouble. So, before I get into the software, let me mention a little lesson learned when we implemented the first version of the software for this temp sensor. So our first software attempt on this, I used the SQLite Python module for storing the temperature data. And I really wanted very accurate timing, so I was saving the temperature data very, very frequently. There's a problem with this. SD cards like the ones in the Raspberry Pi can only handle a limited number of writes before they wear out. And worse yet, databases like SQLite, SQL databases overall, emphasize data integrity. In other words, they make sure that if the data is written, it's written. And if something interrupts it in the middle, it can undo the thing and put it back the way it was. The problem with this is, in order to implement that, it actually has to write to the card multiple times every time we add data. And that adds a lot of wear and tear on the SD card. I left the initial version running for about a month, kind of forgot about it, and I came back, and there were all sorts of errors on the SD card, which, of course, I don't have printed here because it wasn't logging them to the SD card because it was broken. The card was totally unsalvageable. We couldn't use it anymore. The other thing was, I wanted to be able to teach and use this as to show people how to do this. And SQLite uses structured query language. So, which makes it a little hard to use. I switched. Well, first of all, we got to take into account the limited lifespan of the SD card. Now, mind you, we could have just logged the data to SQLite less frequently, and that would have basically fixed the problem. But I decided to change technologies. I use this technology a lot at work. It's a technology called Redis. Now, the reason I switched to Redis is it generally emphasizes performance. And in order to get the performance, it stores data to random access memory, the memory where your program is running. It will write out to the flash or SD card, but how frequently and how aggressively is actually configurable. It also supports very easy replication of our data to another computer, which is really nice if we have like a Raspberry Pi that's running off a battery, and we don't want to have to go and find it and fix it to get the actual data that it logged before the battery died, for example. But the best thing is, it's really easy to know and learn if you already know Python. The reason for this is Redis stands for Remote Dictionary Server. How many of you know what a dictionary is? Right. We're talking about, it is a program that stores dictionaries separate from your main program. These dictionaries then can have things like list, strings, sets, and other data types that we're familiar with. So if you're familiar with the concepts in Python, you're going to find that Redis is generally pretty easy to understand. So setting up the software, I'm using 3 different Python modules for this, the Redis Lite module, the Redis Collections module, and the Bottle module. Every single one of the components I'm using for this is either pip installable or included in the Raspbian Raspberry Pi distro. So now we have a sensor wired. It's now time to write some code to use it so we can actually see it. Now I'm going to do something here. There we go. Thank you, Jupyter guys. So the driver we're using is what's called a kernel driver. And what it's going to do is it's going to create a virtual file. This is actually the file in question. It looks like this. It has a whole bunch of junk in it. But the key thing is inside this file there is a t equals and a value. That value is actually the temperature read by the sensor multiplied by 1,000. So all we need to do to read the temp data is to open that file and get that number, convert it to a float, and divide by 1,000. So we have a very simple bit of code here. We got a function called readTempC. It opens the file. It finds the line with the t equals. It grabs the number after the equal sign, and it divides by 1,000, and then returns it. Very, very simple. And that's all involved in actually reading the data from our temp sensor. So now we can get a temperature. But we also want to store it because we want to be able to do things with it, see how fast the temperature is going up, calculate averages, and things like that. So this is where Redis comes in. Right here, we're getting a connection to a Redis server. So we're getting a connection object. We're telling Redis to store our data in this file here. It will, like I said, do it about every 15 minutes. We want it to be accessible on the network. Redis doesn't actually have to be on a network in order to function, and the default is it's not. But we're going to use the network in a minute. And of course, if you put your Redis server on the network, you probably want a password, so we specify one. Next, we're using the Redis Collections module, list object. We pass it a Redis connection, and we give it a key name. And it will return an object that acts like a Python object, but is storing its data in that key in the Redis server. And this is significant because the Redis server is going to provide us with data. The data is going to be stored in the Redis server, but also Redis will allow us to write separate Python scripts to access the same thing. And then finally, once we have a connection, we read the temperature, and we append it to the list. That's it. And then we sleep a second and read it again. So we're doing one temperature reading a second. And if we run this, you'll see that we're getting temperature data because I'm running this live on a Raspberry Pi. If I put my finger on the temp sensor, you'll see that since my body temperature is warmer than the room, the value will start to increase, and when I remove my finger, it will start to decrease. So now we're logging temperature data. We have a complete Raspberry Pi-powered temperature logger. That's pretty cool. We did it in, 20 minutes. Now, very commonly, we want to do a web interface. So how do we do that? Well, I'm going to use the Bottle library because it's basically the most minimal Python web framework I know of, and it allows me to put the whole damn thing on a single slide. That is the web UI. It's really simple. We're using the same Redis connection. We're accessing the same list object, list key, in the Redis server. So that means that logger, which I left running a minute ago, is still logging data every second. And the most recent temperature reading is going to be the last item on the list because it's appending. So we define a route. So if we go to this, the root route is going to give us the number of temperature readings because it's going to give us the length of that list. And it's going to give us the last temperature reading, which is the current temperature. And if we run this, Bottle is going to give us a web server. And if we go to that web server, you'll see that we have 2,098 readings. And I don't know why I can't read it. And of course, if I reload the page, you'll see the number of readings and the temperature changes. So now we have a temperature sensor that's logging, and we have a web server. And we're, 22 minutes in. Now, like I said, Redis has some really powerful functionality. So here is something that looks a lot like the thing we just did, right? The web interface. This IPython notebook shell is actually running on my laptop. And the only real difference between what we were just running to provide the web UI on the Raspberry Pi and what I'm running on my laptop is the configuration for Redis. We're telling it we want the Redis server on my laptop to be a slave of the Redis server on the Raspberry Pi I'm running. This will replicate the data from the Raspberry Pi to my laptop, which has a real hard drive in it, so it's not going to wear out like the flash card on my Raspberry Pi. It also means if my Raspberry Pi's battery dies, I can still access the most recent temperature reading, which is really cool. So you see, the output looks just like when we were running on the Raspberry Pi. And since it's replicating the data to our server, if I reload the page, you'll see the number of readings increasing and the temperature changing. The interesting thing is, I got a Raspberry Pi here. If I unplug the network, I can reload the page, and you'll see that it's no longer increasing the number of readings, and the temperature's not changing, because, of course, without a network, I can't get any more changes. The interesting thing is, if we plug our Raspberry Pi back in, and I'm pretty sure I'm going to also have to reconfigure the network interface. Thank you. It disconnected. Okay. 5 minutes. Okay, well, my network connection is not coming back up. But if it had, what we'd see is when the network comes back up, all the temp readings that were logged by the Raspberry Pi while the network was down will be automatically replicated to the server running on my laptop. This is really powerful. The other thing is, of course, we could have it replicating data from more than one Raspberry Pi. I don't know why this just started over. Okay. So, going further, like I said, we could replicate data from more than one Raspberry Pi to add more sensors. Now, I'm doing a next version of this, and we're using what's called a microcontroller. This is running MicroPython. So it's an Internet of Things device running Python as well. This thing doesn't have very much or very powerful processor or a lot of memory. But what it does have is built-in Wi-Fi. It's cheap, and it will run nearly 10 times or one order of magnitude longer than a Raspberry Pi. A battery that will run a Raspberry Pi for a day will run this thing for a month. The difference in power consumption is pretty dramatic when we want to actually run on a battery. And for Internet of Things, that's really interesting because Internet of Things you'll frequently find there's trade-offs. Right? Depending on what you do, you may want something that you can sew into your clothing, and size, weight, and power consumption are important. Oftentimes more important than how powerful the processor is. So it is really a good idea to actually look at other options in addition to the Raspberry Pi. There are a lot of options for doing Python Internet of Things. But the Raspberry Pi is a great place to get started. So a little bit for more information, there are a number of component vendors that sell Raspberry Pis and the components for doing Internet of Things with them. They have hundreds of tutorials with step-by-step instructions and pictures and great ideas. This can get you inspired, and you can do amazing things with Internet of Things. You can do almost anything. And of course, with things like Python for microcontrollers, it moves it into a whole new domain. I want to finish off by saying we're going to have an open space today at 4 o'clock, so if you have any more questions or you'd like to learn more, feel free to come by. I'm going to be here for the sprints as well. I don't know if we really have time for any closing questions. I think we're pretty much done. But thank you for your time. I hope you were as inspired as I was to do amazing things with Internet of Things with Python.
So we have time for 1 or 2 questions.
I have a question. I didn't know we had time. Hi, Dwight.
Yeah.
Great. What happens